Okay, let's jump in. Our quick look at the calendar. Last time we had our introduction to derivative formulas, our first shortcuts for finding derivatives. And then we stole a little bit of yesterday and started today's class, which is about polynomial optimization. To optimize means to make something as good as possible, right? And as good as possible more generally means as big as possible or as small as possible. And so that's where we were talking about the absolute extrema of functions, highest point anywhere and lowest point anywhere. A reminder again that our very next class coming up on Friday is our project check-in day. I have no agenda for that day. That is just going to be a day for you to work with each other, work with me on either or both of the two projects that are outstanding. And one last plea, try to get as much of those projects done between now and then so that you can get as much help as possible on the harder parts of the projects, which are later in the projects, all right? Technically, by the end of today's class, you have all the tools you need to do everything in the projects. All right, a note about the quiz. So you saw this if you read the syllabus carefully, but all 4 of our quizzes this semester are take-home quizzes. And so I will hand you this take-home quiz at the end of tomorrow's class, but here are the directions just so that we're really clear on exactly what the rules are of this take-home quiz. You can use a scientific calculator, not a graphing calculator. If you need to borrow one from me, let me know. I'll lend you one for the weekend, all right? Not a graphing calculator, but a scientific calculator only. You can also use a 3x5 index card with anything written on it you want. Definitions, theorems, problems worked out, lyrics to your favorite jam, anything you want. Something to keep you motivated through this take-home quiz, but you got to make sure you make that index card before you start the quiz, right? It's not about like, look at the quiz and then decide, okay, apparently I need these tools, so make the index card first. You cannot use any other resources like your textbook, other notes, a graphing calculator, or people. You can take up to double the recommended time limit. Here is the recommended time limit for this quiz. It's 24 minutes. You can take up to 48. If you're really on the ball, you should be finishing this thing in less than 24. But I want to make sure everybody has an opportunity to show me everything that they know, okay? But up to 48 minutes. And we're trusting you on your honor in terms of not using illegal resources and in terms of not using more than the recommended amount of time. And so you are going to write your start time and end time right there on the quiz. Questions on the rules? Okay, so I'll give this to you. All the directions are written there on the quiz, so you'll have them in front of you tomorrow. Yeah, the 3x5 index card is something that you can use to write anything that you want that might help you on the quiz. So if you want to write the power rule on the quiz, or on the index card, you can write it, and then you can use it during the quiz. So if there's anything you think you might not be able to memorize or remember, you write it on that index card, okay? I have index cards in my office. Let me know if you want one. Other questions? Yeah. Front and back. Other questions? Okay, good. So like I said, we start here on page 42 with a very quick recap of what we did last class at the end of class. We had a graph. We talked about the local maxes and the local mins. These were points that were higher or lower than every point nearby. They're colored up here in blue and red. And then we talked about just looking at the green part of this graph, just from here out to here. And we talked about finding the global max and the global min, the highest point anywhere. This point right here is a local maximum because it's higher than all the points nearby. But there are higher points on the graph, so it is not the global maximum. The highest point on this, kind of green highlighted section was right over there at J. And the lowest point was right there at D. And so we discovered last class that if we're looking for the highest and lowest points on a closed interval, there's only 2 places you need to look. What is point D called? It is a minimum, but it is a critical point because it's a place where the tangent line is horizontal, right? Critical point because the tangent line is horizontal. So the critical points or critical numbers are good candidates for maxes and mins. What's the other candidate for a max or min? Is the endpoint. So all we had to do to find the absolute or global extrema of a continuous function on a closed interval was written up here in 7. You're just going to evaluate the function at the critical points and at the endpoints. Pick the highest and lowest numbers and you win, okay? So something we're gonna do repeatedly this semester, but I just wanted to remind us, this is where we ended last class. Okay, so moving on to the next page, I'm gonna take a look at number 9. Can we go to Wayne?
Here is our first of many optimization problems. It's 30 inches of matter margin on the sides. Find the dimensions of the page part of the part of the page.
Okay, thank you. So on the next page or the one after, there's a step-by-step process written out for how to solve these kinds of word problems. They're called optimization problems because they involve either finding a maximum or a minimum. You're going to read that later today, but let's just walk through it together here on this particular problem. So one technique to begin is to just draw a picture, try to get a handle on what's going on here. So there is my piece of paper. And on part of this piece of paper is printed stuff. And then around the edges, we've got the margins. So I'm going to draw inside here some smaller rectangle. And that's where the printed stuff is with blank space all around. Okay. And now we're going to start to use the information from the problem to continue labeling our diagram. It says 36 square inches of printed matter. Is that the entire rectangle or the inner rectangle? That's the inner. So I'm just going to make a little note to myself. The area here, it's got to be 36. And then it says 1 inch margins along the sides. So that means from there to there is 1 inch. And the same thing on the other side. 1 inch that way. And then the top and bottom margins are apparently a little bigger, 1.5. So 1.5 top to bottom in 2 different places. And then finally, the hint here is to let L and W be the length and the width of the part of the page that's printed on. Again, is that the whole thing or the inner? Inner. So we got an L, which I'll call this side right here. And then a W for the other side. Translating all of that to this picture is a big part of the problem. So really take your time as you set up the picture. Questions on the picture? Okay, so let's get to the heart of the question. It says find the dimensions of the page that will use the minimum amount of paper. Give me a math word to substitute for amount of paper. What math thing are we trying to minimize? Area. Right? That's what we're talking about, is the area of the total amount of paper here. So it feels like we got to start there with a formula for the area of the whole page. That is the thing we are trying to minimize. Okay, so the whole page is a rectangle, so it's the length of the big rectangle times the width of the big rectangle. The length of the big rectangle, going from here to here, includes the green L plus how much more? Plus 3 more. So L plus 3, which we'll say is the length of the whole page. And then times the width of the whole page, which is here to here, which includes the W plus 2 more. So W plus 2 is the width of the whole page. That is the thing to be minimized. Now just thinking back to the graph we saw at the top of the previous page, you're just imagining some function going up and down. And what's true at all these points that are at the high and the low? What's special about them? They're critical points. They have horizontal tangent lines. So what we're about to do is something we're going to do over and over this semester, is take a derivative and set it equal to 0, the slope of this horizontal line. The problem is, how many variables are on the right-hand side of this function? 2. We only know how to find derivatives of functions of one variable. In Calc 3, we'll talk about finding derivatives of functions of multiple variables. But at the moment, we have to get rid of one of these letters. And we haven't used this important fact over here, that the area of the printed page is 36, and so we can translate that into an equation. Area of the printed stuff is 36, but in terms of W's, in terms of letters, it's L times W, right, for the inner rectangle. Okay, so we can take this equation, the last one, solve it for one letter, and then replace that letter in the original equation. That's how we're going to get the L and W from the first equation down to a single letter. Okay, it makes no difference which one you solve for. I actually did this beforehand, and I'm going to save us a little bit of time on some calculations. I solved for W. So W is equal to 36 over L. And so then our whole page formula becomes, so we're just copying it as it is with all those parentheses, but the single W is about to get replaced. So L plus 3 gets copied. W plus 2 becomes what? 36 over L plus 2. And why is that function better than the top one on the page? It's a function of one variable, no longer two. Okay, great. So what we'd like to do is take a derivative of this thing. At the moment, we don't have a way to take a derivative of the product of two functions. So the only recourse we have is a little bit of algebra before we do our calculus. So let's FOIL that together. So first, what do we get? 36, right? Because the L's cancel when you multiply the first. Plus outers, 2L, plus inners, 108 sounds good. Divide by L, plus the last, 6. And so we'll just combine the 36 and the 6 to get a 42 in the front. Okay, now it's in good shape for us to take a derivative and set it equal 0. Okay, using good notation here, A and then a little apostrophe will represent our derivative, A prime, just like F prime. All right, now using our shortcuts, what's the derivative of 42? 0. Derivative of any constant is 0. You don't need to write it, but I'll put it so it's there, 0 plus. What's the derivative of 2L? 2. It's one of our special cases. A constant times x is just the constant. And then 108 over L is actually another one of our special cases. If we're willing to memorize it, it's a constant over x. The derivative was negative the constant over x squared. So negative 108 over L squared in this case. It's okay if these new derivative rules are not on the tip of your tongue. With practice, like everything else, they get easier. Okay, so we've got our derivative. Very common to take it and set it equal to 0. It's our way of seeking out the places where the tangent line is horizontal. So let's go ahead and subtract the 2 from both sides. So it's negative 108 over L squared equals negative 2. We can clear that fraction by multiplying both sides by L squared. And then 2 more steps to solve for L. Divide by that negative 2. And then take the square root of both sides. Technically, what do we need to put in whenever we take the square root of both sides of an equation? Plus or minus. Put it here, and then I'll say, okay, definitely the length can't be negative root 54, so we'll reject that guy. If you forget to do that, will I take points off? Probably not, but it depends on how I'm feeling that day. I don't know. But root 54 is our only, what's it called? Critical point. Or critical number. Okay, now we're going to do something kind of funny. All we know is that if the length is root 54, then this area function, which might go up and down like the picture on the previous page, is horizontal at that spot. Root 54 is, I don't know, like 7.5, something like that. Right? So if you're at length equals 7.5, then the area function is horizontal. Does that mean that the area function is at a minimum? Is it guaranteed that the area function is at a minimum because it's horizontal there? Couldn't it also be at a maximum? Right? All we're doing is finding a place where the thing is flat. So we don't know whether that is a minimum area or a maximum area piece of paper. We're hopeful that it's a minimum because that's what we're after, and root 54 is the only answer we have. So probably because this is a math question, that's the answer. But we got just a tiny bit more calculus work to do to justify that it's a min. So for the first time, is it a min or a max? So for the first time, we're going to use something called the sign test in this class. You might have seen them in other contexts in other classes. That's what we're going to do. We're going to put root 54 on a number line. And just so that we're, what, 7 point, so about 7.3. And then we're going to put the real world domain of this area function. What's the smallest the length could possibly be? The 0. All right, so 0 is the end. And could it be 0? Probably not, but you know, like you can't put any other number there. So 0. Is there a maximum? Is there like a cap on the length? Could the length be like, could this paper be like a mile long? Yeah, what would the width have to be for there to be a mile long piece of paper? Like something really tiny, but you can make a really, really tiny width paper that's a mile long and still have it be 36 square inches in the printed part. So there isn't any upper bound here. So that's it. Question? Brendan? Andy?
An infinite paper direction would have to be small the other direction.
That's right. But there's no number that we can put out there to cap it. It could go forever. Okay, so here's what we're going to do. We're going to label this number line with a function. Now, there's only 2 important functions up on this page. One of them is the area of the whole piece of paper, and the other one is the area prime function. Which was the one that the root 54 came from? Did it come from the original, or did it come from doing something with the prime? It came from the prime. So that is the label that needs to go on this number line. We're doing a sign chart on A prime because that's where the root 54 came from. And all we're going to do is take a look at this little truncated number line, and we're going to pick a number in each of the intervals that's up here. So any number between 0 and 7.3, and then separately any number bigger than 7.3, and we're going to plug those numbers into A prime. And we're just going to write whether the sign is positive or negative. So let's pick a number that's between 0 and 7.3, for example, 1. Typically, I wouldn't do this. I'm going to kind of put it like way down here, and I'm just going to write L equals 1 is the thing we're testing, but usually you wouldn't even bother putting that. You would just keep that in your head. And we're going to plug L equals 1 into our A prime function. So it says 2 minus 108 over 1 squared, right? Just plug 1 right into that function. 2 minus 108 over 1. Don't do the arithmetic. Is it positive or negative? It is very negative. Yes? It's 2 minus 108. So turns out if you pick any number between 0 and 7.3, you would have gotten a negative number. We picked 1. We could have picked 7.2. It'd still be negative. Anything in there. And now we pick a number that's bigger than 7.3. So a lot of people like to pick numbers that are close. You know, like what might you pick is like the next, like 7.4 or 8, right? I don't do that. We're picking 100. If you pick something that's close, but what if you put 7.3 into the area function? What would you get? What did we do to the area function where 7.3 popped out as the answer? We set it equal to 0. So if we put the 7.3 in, we're going to get 0. So if you put 7.4 in, you're going to get something really close to 0. And if you make a small arithmetic mistake, you might put the wrong sign because the answer is close to 0. I'm going to pick a number that's not even close to 7.3. I'm going to pick 100. There's no way I'm going to mess up the arithmetic here. In fact, I'm not even really going to do the arithmetic. No calculators. We're plugging 100 in for L. This is 108 over 100 squared. That is very close to what number? Very close to 0. Agree? And then I'm doing 2 minus something that's pretty much 0. Positive or negative? Positive. Whereas if you tried to put 7.4 in there, I would have a hard time doing that in my head. So you're relying on the calculator, and maybe we punch a button wrong and we don't catch the error. So pick a ridiculous number, and typically makes the calculations easy. Okay. So what we saw, one thing did you guys write this last class? I feel like we wrote this at some point. If the derivative is negative, then what kind of, like what is the function doing if your derivatives are all negatively sloped? Then your function is going down. It is decreasing. And if your derivative is positive, then the function is increasing. So what we're looking at here is that A prime goes from negative to positive right there at the 7.3, which means the A function, the original function, goes from doing what? Decreasing to increasing. And if you have a function, just imagine, decreasing to increasing, what are you looking at? At the critical point, you're looking at a minimum. And this is the calculus justification that we've actually found a minimum. So I'll just write the sentence, and you'll get used to writing sentences like this. Since A prime goes from negative, I'll abbreviate that, to positive, I'll abbreviate that too, at what number? Yeah, let's be really precise here. At L equals root 54, A has a min or max? Min. At L equals root 54. That is a full-fledged justification. Sign chart by itself isn't enough. You got to tell me you understand what that sign chart represents. Okay, so you are going to go on to the next page. and you're going to work through problems 1 and 2 there. And then I made some notes, some small changes on the page after that. I think somebody got it at each table, and see how far you can get.